Now we have concluded everything that we need to run a first simulation and extract useful information from the output files. What I want to do in this video is to do one step further. So let's imagine that we created our structure, we got to an optimum structure that we consider sufficiently nice, but now we want to check how would the same structure respond in terms of force displacement curve if instead of loading it vertically, we were loading it horizontally. So now, in this case, we don't want to optimize the structure to an horizontal displacement. What we want to do is simply to see what would be the force displacement curve of the structure that was optimized for a vertical load if we were to apply to the optimum structure a horizontal force, a horizontal displacement instead. So to do that, what we want to do is to create a new input file where this time we are loading the last configuration from the previous simulation and using this last configuration as the initial one and imposing on this last configuration a horizontal displacement instead of a vertical one. If we do that, then from the first optimization step in the thermal, we will be able to extract the information to obtain a force displacement curve. It's easier to show it than to say it. So how do you do that? A follow-up simulation. Well, let's create another folder out here maybe, and let's call this example 2. What do we need in this example 2? Well, we'll certainly need an input file and executable, so we can copy both of them and put it there. And then we will need the DETO dump, because what we are going to do is take the last configuration of that one and import the optimum structure from that. So we copy this. Well, actually, we don't need to copy it. We can give it as a path. We will leave it here. So in this x2, we open the input file and we start to modify it to do what I've just mentioned that we want to do. So there's nothing much that we need to change here really. The geometry is still the same. We are working with the same base structure made of the same particles. What we need to change is that we don't want to start with a uniform distribution of chi, but we want to load the distribution of chi from an existing dump file. So to do that, instead of using this command, which we can comment out adding an hashtag in front of it, we put this other command, init chi file, and then the name of the file. The name of the file is one folder back. Because we are in x2, we need to go one folder back in the folder example, and then the name of the file, dump, DETO.dump. Then we need to give the entry. So what configuration do we want to extract from this DETO.dump file? Well, in our case, we want to extract the last one. So what is the last one? Well, we have to find a good way to do that is to use, for example, a search option. So you can search for the keyword time step. And then you see that we have 17 of those, and you can go to the last one. You see that we are moving down with this sidebar here, and this is, where is the last one? Okay, oops, too much, one back. This is the last one. It was time step number 16. Is the last entry, the last frame that we save in Ovito. You can also find this by opening it in Ovito. Let's do it. So we have it. You can just open the dump file, replace selected. You see that the last frame is 16. So you want to take the structure from frame 16, this one, and apply a horizontal displacement to the top instead of vertical. So we load with this command, initialize the chi distribution from this file here, entry number 16. Then the rest can be exactly the same as the previous simulation. It's still going to be an optimization, but actually we will stop it after the first step because we don't want to re-optimize the structure with the horizontal load. We just want to extract the force displacement curve, so we don't let chi be redistributed. So what do we do here? We leave everything the same except for the fact that we don't want to set a vertical displacement anymore. we want a horizontal displacement. So it's as simple as saying displacement x, 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 x. So now we are applying a displacement of negative, let's put it positive 0.5 millimeters, so to the right, and maybe let's make it a bit bigger. Let's make it 1.4 millimeters. Okay, so we are displacing the top to the right by 1.4 millimeter with this strain rate. Supports are the same, we are fixing the same supports. We don't want to fix anymore the X position of the top, otherwise it will not move, so we have to remove this anti-tilting fix. And what else? Thermal. What do we want to put in the thermal? Well, in this case we want to get a horizontal force versus horizontal displacement curve. So instead of Fy, we can fix X as a displacement, as a position, and Fx as forces. Okay? So we prepared an input file to load the system horizontally, and then pretty much the code will try to re-optimize the structure for this load starting from the last configuration of the previous solution, but we will stop it early not to let it optimize it too much. We only care about the initial response before the optimization actually starts. So at the first step. So we can go to cd ... goes one folder back. Now we are in tutorial DETO. So we're in this folder here. And then we do cd ex2 to enter the new folder, or you can right click on the folder and open it in a new terminal. So if you do ls here, you see that we are indeed in this ex2 folder, and then we run the code as usual. /input DETO2D, input DET, enter. And now it's saving. In this case, it is important that we save the old dump so that the option, sorry, wrong file, that in this input file you must make sure, because you want to create a force displacement curve, you want to make sure that this option here is yes. And now you see that it's accumulating steps. It's taking its time. We have imposed 1.4 displacement. Before we were doing 0.4, so it will take we are using the same rate, so it will take a few more steps to actually conclude the loading stage. And what we care really is about these results that are being recorded now in the thermal hall for the first step. So when the first step will be over, then the system will redistribute Xi, but at that point it's starting actual optimization. We don't want to optimize the system, we only want to record force displacement in shear for the final structure from the previous optimization. So we only care about the results on the step 1. So what I will do now, when the step 1 is over, I will plot the results. I will show you the dumps and the content of the thermos, but I will still leave the simulation running just for curiosity to see what comes out as if you start a new optimization from the end of a previous optimization, which is something that you may want to do at some point. It's something that you can often do in case you, for instance, for any reason a simulation crashed, the computer turned off, and you want to restart the previous optimization, not from the beginning, but from the latest result that you obtained. Well, you can use exactly the same technique by imposing the same displacement, all the same conditions except of initializing the Xi from the previous dump file instead of initializing it from a uniform distribution. So it is taking some time, but what you are seeing here is that now this column here, which is the energy, is decreasing, so we probably overshot quite significantly the maximum, and now it's trying to get back to an equilibrium position. While this is grinding numbers, we can actually open the dump file in Obito, so load file. We need to navigate to the new folder, ex2. We pick the old dump, open it, replace selected, and now we have this last structure from the previous case that is being progressively loaded, as you can see, in shear. So it's being sheared on one side. It's also tilting because I'm not telling that the top particle have a fixed Y position. If you want it to be pure shear without any, or simple shear without any vertical displacement, without any tilting, then you should also add in the input file the vertical position of these top particles. So you see that the system is doing what we want. We can also color code the deviatoric stress to try and see if there is something interesting. We can adjust range for all the frames, so it computes automatically the color code scale, and then if we run this, we can see how the shear is generating stress, deviatoric stress in the system. We could also plot the hydrostatic stress instead, so which highlights compression, regions in compression and regions in tension. And you can see that the hydrostatic, as you expect, tells you that the right part goes in tension, the left part goes in compression. You can also reduce a little bit the scale to see if there is any interesting heterogeneity through the structure. Not yet. 0,2 minus 0,2 starts to see a bit more. So you see that there is compression not just at the very bottom, but the region on the left is in tension, the region on the right is clearly in compression. Okay? So you can play with the edges to try and highlight a bit more the stress distribution. Let's see if it proceeded at all. We can run an update. And you see that indeed, probably a second step started because it went up to this point and then it went back. And when it goes back, it's because the system is actually now trying to optimize the structure given the new distribution of load that we gave to it. This is not the point of this exercise. We just wanted the first step, so up to here, before it jumps back, because this is what we can use to now draw using Excel the horizontal force displacement curve for this structure. And this is telling you how well is the structure that was optimized for compression behaving under shear, which is an interesting design question that you may want to ask yourself. So let's see the Excel file for the thermo-O. So let's open a new sheet here. We open the thermo-O file. We select everything with Ctrl-A, Ctrl-C, Ctrl-V. Import wizard. Finish. Again, we define a column called displacement in millimeters, which is the current particle position minus the initial one, with the $sign, the initial one. We drag to the bottom of this file. And then we define the force total, kilonewton, and this is equal to the sum of all the forces that we recorded at the top, because these are the particles that we are displacing. We drag down, and once again we see where the first loading stage finishes, and it's here where the new zero starts. So we select the displacement for this column, and we select the corresponding force as well. We drag down until finding the next. Oh, sorry, I overshot these, and we select until the next zero. Insert points and lines, and this is the curve that we obtained. The force is negative because what we are plotting here actually, I forgot to mention in the previous video, is the reaction provided by the particle. So if you want to see the force that we are applying, actually you should put a minus sign. The same was true for the previous video where we had the positive force in Y, which means up, and that was the reaction of the particles that were trying to contrast the vertical displacement we were imposing. So now that we put the minus sign, we get all these being positive, and this is the kind of response that we get. You see, it is linear, but there is also this initial step that is non-linear. But this non-linearity is due to the fact that we are imposing probably a strain rate that is too fast, but in the end, when it gets to the 1.4 millimeters that we wanted, it realizes that it overshot and it relaxes back. So indeed, if you draw a parallel line to this one from 0 to here, you're going through these points exactly. So whatever nonlinearity was accumulated by the excess rate at the beginning is then relaxed back at the end of the simulation. So in this case, we can consider the rate that we applied reasonably okay. Just out of curiosity now, since the simulation has advanced a little bit, we can again take the content of the thermal and paste it into this table A1 with the wizard finish. Okay, and we can drag to the end this displacement and total force that we are recording. And then we can add to the graph. Let's see where the second step is starting. It was starting earlier. I'm looking for the 0 here. Okay, this is where the second step is starting. So we can select data, add a new series, start from the new 0 here, and select all the data that we gathered from the second step. Select the corresponding y values, again from the new 0 to the end of the second step. Okay, and now we can see how the curve looks after we are trying to actually optimize the structure to this new loading condition. And you see it didn't change much. And the reason is because we started already from a configuration that was quite settled, with all the particles being, if we go back to the chi distribution here, all the particles were pretty much 1 or 0 except for the two lateral arms. We'll put it in black and white for clarity. So there is not much possibility for this structure to massively redistribute its mass through these lateral arms here, because these are essentially not stable. They are unable to carry any load, so they cannot accumulate strain energy, they cannot contribute, so it's hard that they are able to attract back mass. But for other types of structures, even if you start from a structure that has been optimized for a loading scenario, if you then start a new optimization on that optimized structure with a different loading scenario, you may change its geometry. So it's something that may be interesting to try in your exercises.